My name is Smirnov, and I'm presenting MarioNette, a self-supervised approach to learning sprite-based representations. This is work done with Michael Gharbi, Matt Fisher, Vitor Guizilini, Efros, and Justin Solomon. A typical autoencoder-style deep network learns to project images onto a high-dimensional latent feature space. While such learned latent spaces often reveal interesting structure in the training data, they can be difficult to understand or manipulate. Instead, we propose to learn a latent space that is explicit and controllable. Borrowing ideas from animation, we consider an atomic unit that is richer and easier to edit than the pixel, the sprite. We invert the process of sprite-based game design in a self-supervised fashion, learning to deconstruct content into a visually interpretable representation. Many recent works have used deep learning to deconstruct visual content. Some automatically split videos into layers grouping motion, and others, like slot attention or space, discover objects without supervision. These methods, however, struggle to decompose images with very large numbers of repeated elements, and they do not produce a single unified dictionary, which can be useful for downstream applications such as content editing or retargeting. In designing our approach, we take inspiration from works in image compression like image epitomes or déjà vu and digipaper, which aim to establish an explicit link between an image and its repeated parts. Given a dataset of frames from a single source, our system jointly learns two components. First, we learn a dictionary of sprites, square RGBA texture patches. Using an alpha channel allows us to reconstruct content with multiple depth layers. In addition to the sprite dictionary, we learned a model that encodes a single input frame into a grid of latent codes organized into multiple depth layers. Each grid anchor gets assigned at most one sprite from the dictionary, and the sprites can be locally translated by a learned offset. Thus, we obtain several sprite layers, each with a transparent background. The layers are then composed back to front onto a background to produce the final reconstruction. Our sprite dictionary is made of a set of learned latent codes. The codes are passed through a fully connected generator network to obtain RGBA texture patches. We process each input frame with a fully convolutional encoder, which downscales the image to produce a coarse grid of anchors for each depth layer. Each anchor is assigned a latent code as well as a probability value corresponding to whether that anchor is active. Having obtained a set of latent codes for the dictionary sprites as well as for the frame anchors, we pick a dictionary sprite for each anchor using a softmax over dot products between the two sets of codes. We place a sprite at the center of each grid for each anchor that is active, that is, having a high probability value. We then apply local learned translations using a spatial transformer. This allows us to place sprites anywhere on the canvas, not just at cell centers. Shifting the sprites can cause overlap within a single layer. When this happens, we randomly choose an ordering. This random permutation encourages our model to either avoid overlapping sprites within the same layer, or make the sprite colors agree in the overlap region, since these are the only two options that yield the same rendering regardless of the random Z ordering. Note that sprites on distinct layers are not shuffled. The shuffling simply prevents the network from abusing the compositing to cover patches with others from the same layer. Finally, we composite the layers from back to front to obtain a reconstruction. We train our network in a fully self-supervised end-to-end fashion by computing an L2 loss between the input and the reconstruction, as well as some additional regularizers. Here we show our results on frames from a level of Super Mario. Our model successfully disentangles foreground from background and recovers a reasonable sprite sheet. Having reverse engineered the game, we can use their decomposition for applications like editing. We also deconstruct Atari's Space Invaders. Since this game does not contain overlapping content, our model only needs a single layer. For Fighting Hero, in addition to the sprite dictionary, we also learn a background texture to capture elements that cannot be easily explained using sprites. This can be thought of as a special sprite of resolution greater than that of a single frame. To our knowledge, no prior works target differentiable unsupervised sprite-based reconstruction. As the closest baselines, we compared two state-of-the-art methods that obtain similarly disentangled representations. Slot attention decomposes each input frame into 7 layers or slots. While the inputs are reconstructed accurately, the decomposition across slots is not semantically meaningful. Space decomposes each frame into 3 background layers as well as a foreground. Again, the reconstruction is faithful, but only a few sprites are recognized in the foreground. In contrast, our model is able to capture each repeated foreground element as an individual sprite in the dictionary. To further evaluate our method in comparison to space, we deconstruct a synthetic game dataset for which ground truth positions are known for every sprite. Again, while space only recognizes several sprites, we are able to learn each ground truth sprite. We quantify this by computing the intersection over a union induced by the space foreground-background segmentation and ours. Our IOU score is over 20 times higher than space's. To show that our model learns more than simple motion features, we also compare to 2 conventional non-learning baselines. We compare a segmentation of the frame obtained by clustering optical flow directions using k-means to one generated using our decomposition. The flow-based approach is unable to capture many of the details in the frame. We also show a dictionary obtained using an online dictionary learning method. Because this method does not have the inductive biases of our model, the resulting dictionary is not easily interpretable or editable. Although our model is designed with sprite-based animation in mind, we show some preliminary results on generalizing to natural images and videos. Here, we train a model on a tennis video. The model learns parts of the player's body as sprites and captures most of the tennis court in the learned background. By simply selecting the player's sprites in the dictionary, we can quickly obtain a coarse segmentation of the entire video clip. Our model can also discover recurring patterns in a single natural image. We train on random crops of a photograph from the 2013 US presidential inauguration, which contains many repeating elements like stairs, columns, and people. With a dictionary of just 39 32 by 32 sprites, we recover much of the detail of the original 400,000 pixel image. We show some limitations of our approach by applying it to automatic font discovery. We train on random crops of pages of Moby Dick. Here, each input frame consists of many densely packed sprites, and many individual glyphs consist of smaller repeating elements. We suspect that because of these issues, combined with the lack of motion cues between frames, we do not achieve a perfect reconstruction, learning certain sprites with multiple glyphs and others with just partial glyphs. Our results on natural content motivate some exciting next steps for future work. By expanding the range of deformations applied to the dictionary elements, such as appearance or shape change, we can more flexibly accommodate natural data. Another interesting direction is using our sprite-based decomposition to discover relationships and interactions between sprites. We could also consider learning the dynamics of sprite motion within a video sequence. In conclusion, we propose a self-supervised method for learning an explicit and controllable sprite-based image representation. This representation is intuitive and convenient for downstream applications that require editability. Thank you for your attention, and please check out our code on GitHub.